Okay, what we're going to do over the next couple days or so is just kind of use density. Now, I know you've been taught density before. I'm sure you're probably sick of it. I know I don't need to sit there from the beginning and teach density from scratch. However, there are kids at different levels, so here's your intro so everybody knows what we're talking about when we come into class and start using this in the future. Alright, I want you to try the first three problems here, number 1, 2, and 3. Give that a shot, and then pause it, and then come back and we'll just take a peek at the answers. Alright, so I hope you've given this a shot already. In the first example, you've got 5 people in a closet, 5 people in a classroom, and 5 people in a gym. So the people are the same. In this case, the mass or the people are the same, and the volume changes. Remember the little delta is a change sign? So the volume changes. So the size of the space is different. So therefore, as long as one of the variables is the same, in this case people, we can easily determine where the people would be most dense or squished closest together. And that would be in the closet, and least dense, they have the most room to spread out in the gym. The next one, the people stay the same. I'm sorry, the size of the classroom stays the same, but the people change. So the volume is constant, but the mass, the amount of matter, amount of people change. So we've got most dense, 145 people in a classroom would be ridiculously dense. People would be shoulder to shoulder, and least dense would be 15 in a classroom. They'd be able to spread out a lot more and have a lot more space in between them. And then it says the above questions were easy to answer. Why is the following question not easy to answer? Well, 3 people in a closet, 20 people in a classroom, 80 people in a gym. We don't know how big those closets are, those classrooms, those gyms, and so forth. So we have a hard time making a quick judgment on which is most dense or least dense because both variables change. It would be great if it was one of the questions above where either 5 people stayed the same, or we always had the same mass or same people, or in this case, the classroom stayed the same and we always had the same volume. Those are easy to deal with, but because both variables changed, we have problems trying to answer and make comparisons between this problem here. Then it says, what value must you know? You need to know what the volume or the space is. How big is, how many square feet or how many square meters is that closet or that classroom or that gym, and then we can do some math and make some comparisons. Now it says density is a comparison between the amount of matter and how much space. Amount of matter is another name for mass, and the amount of space something takes up is volume. Hopefully you remember that D equals M over V. Density equals mass over volume. So now let's do some real science problems. Instead of kids in classrooms, let's talk about grams of a substance and the space that it takes up. So look at your first problem, do 6 and 7, and then take a peek at 8. Pause this and then come back when you're done. Alright, so number 6. What's the most dense? Well, we've got 30 grams of a substance packed into 10 cubic centimeters. And over here it's just 20 grams packed in the same volume and only 5 grams packed in the same volume. So B, 30 is most dense. Particles are squished closest together because they're all in the same amount of space. And then C, 5 grams would be least dense. Particles, there's only 5 grams of a substance, so it could spread out. What is kept constant? The volume in this case, and what changed? The mass. We had 20, 35, but the volume was always 10 cubic centimeters. Okay, so that was pretty easy to figure out which is most dense, least dense. And same thing with this one. You should have realized that 20 grams stuck in only 2 cubic centimeters, this little tiny box, 2 cubic centimeters, 20 grams stuck in there. That's really dense, so that's going to be B as most dense, compared to 20 grams, the same amount of stuff, stuck into a huge box. We've got a box that's 100 cubic centimeters, much, much, much bigger. So that same amount of matter, at 20 grams, can spread out. Particles are much further apart. So that's least dense. What's kept constant? Masses are all the same. What changes? Volume changes. So these are easy to make comparisons because one thing stays the same and the other thing varies. Now look at 8. 27 and 22, 104 and 90, 83 and 80, both change. We have 3 different masses and 3 different volumes. So because both variables change, we can't quickly assess and figure out which is least dense and most dense. Both variables change. So we're going to have to do some math. Now the math that you know, hopefully, is density equals mass divided by volume. Take your mass, divided by your volume, get a ratio, and it's going to end up being some sort of number that's many grams over 1 milliliter, or so many grams over 1 cubic centimeter. Okay? When you divide mass by volume, which we said we're going to do, you end up with a value for mass. The volume basically cancels out, and you end up with this being your value on top. Now this is still the numerator at the top of the fraction. The denominator, the bottom of the fraction, this whole volume thing here, automatically becomes a 1. The units don't cancel out, but the number becomes a 1. Now you know anything over a number, or any whole number, is really the same as the number over 1. So 2 is the same as 2 over 1. 100 is the same as 100 over 1. So whenever you see density, you're always thinking that. It's not just 2 grams, it's 2 grams per 1 milliliter. It's not just 100 grams, it's 100 grams per 1 cubic centimeter. Okay, or whatever unit we happen to use for volume. So when you divide through, you get a number on top, and then the bottom is going to be a 1. You must include both the numerator and the denominator when you write your answer. So if you have a problem, it says 10 grams of a substance that takes up 5 cubic centimeters, you're going to do mass divided by volume, 10 divided by 5, and I know you all know 10 divided by 5 is 2, but it's going to be 2 grams over 1 cubic centimeter. Okay, put the 1 down at the bottom. By dividing through, you make the different values for volume all 1. So if we do have different values for volume, they're all going to be 1. And then it's easy to make comparisons because it's always 1. So if you're to look at these problems, you want to determine the mass that's going to be found in just 1 cubic centimeter. We know 200 grams is in 100 cubic centimeters. What's in 1? We know 42 grams is in 7, but what's in 1? 25 grams in 5, what's in 1? And you get the idea. So after we do our quick math here, we realize that 200 divided by 100 is 2 grams if we had 1 cubic centimeter. The one below it, 42 divided by 7 is 6 grams if we had 1 cubic centimeter. This one, 25 divided by 5, is 5 grams if we had 1 cubic centimeter. And 36 divided by 4 is 9 grams divided by 1 cubic centimeter. So we can now easily look at this and say, this one is most dense, and this one is least dense. I wouldn't have been able to make that determination right off the bat that quickly before, when both the mass and the volume were different. But as soon as I divided through, and I made all the volumes on the bottom 1, that's key here, 1 on the bottom, 1 on the bottom, 1 on the bottom, and 1 on the bottom. As soon as I did that, then we were able to easily compare densities. So that's why we have the formula density equals mass divided by volume. We can cancel out the volume and get 1 on the bottom and make comparisons. Now, below is a box that has sides about 1 cubic centimeter by 1 centimeter by 1 centimeter by 1 centimeter, which comes out to 1 cubic centimeter. Now, if we had this little itty bitty tiny box, then we could put 1 milliliter of liquid into it. So these two things are equal, which is what this says over here. You should already know that. If you don't, you know it now. 1 cubic centimeter equals 1 milliliter. So now we can read the density values in terms of either grams per cubic centimeter or grams per milliliter. They're interchangeable. For instance, if 10 gram sample takes up 5 cubic centimeters of space, we also know that it would fill up a graduated cylinder to the 5 milliliter mark if it's something that we could pour in there. Usually volumes are measured in milliliters unless the length and the width and the height are measured. If we measure length and width and height, then we just cube them and we end up with usually centimeters cubed. Okay? The next section is going to deal with actual density problems, most of which you should be able to do without a problem. A couple are going to be a little more complicated because we're not just solving for density. Alright, so let's look at the first one. A liquid has a mass of 63 and it fills a graduated cylinder to the 52 milliliter mark. Why don't you pause this, take a second to do that, and then check your answer. So when you do mass divided by volume, the numbers cancel out, and on top we end up with 1.2, I'll keep 2 sig figs here, grams over, and this is how you have to express your answer, over 1 milliliter. Okay, so that's the density, 1.2 grams over 1 milliliter.